Good morning.
Could we at least
Yeah.
maybe say a few notes about mappings and amplitwist because I'm still kind of confused. I saw what you said on Piazza, but I really just I feel it feels like a lot of these problems is a theme, and I just don't know exactly. Uh, I don't have much experience with this, I guess, but I don't know where it's coming from.
Okay, so everything is based on one magical fact. And the magical fact is that you can define a derivative in two dimensions that doesn't depend on the direction of approach to the point. So, Cauchy-Riemann. So not obvious you can do that because in general, in higher dimensions, derivatives are always directional. They always depend on the way you approach a particular point. So you say, well, let me demand this and see what follows. And out of it follows everything. And the beauty of the result is that integrals can be computed on contours which can be moved around because the direction doesn't matter. So you can move everything around as long as you don't cross any singularities. So everything about complex analysis comes from that fact. And then, a whole course. So I gave you a link to Kontorović course, a mathematics course at Rutgers, which is a very good one. So a whole semester can be spent, all books can be written on consequences of that. And, I cannot do it justice in this course. We're only spending 3 weeks on this, which seems like a lot, but we can spend much more. So amphi-twist, I'm almost sorry I ever used the word because, you're just getting tripped by semantics. It says one of the consequences that derivatives are not directional is that when you look at how they act on infinitesimal objects in a plane, because you're in two-dimensional plane, so you can draw any little figure like a picture of a cat, but infinitesimal one. And one consequence is that the orientation doesn't matter because derivatives are orientation independent. So this gives you the first part of both parts, but first part of amphi-twist is that the scaling, when you measure the slope of something, that's what the derivative does. That's some number. And in two dimension, it should be a matrix with 4 entries because you can take derivatives in two directions of a two-dimensional function. So that's the Jacobian of the matrix, Jacobian matrix for the mapping from small perturbation of the variable into the resulting perturbation function. But because of this directional independence, it doesn't actually matter in which direction you look, which makes the scaling isotropic. So the overall, there's a prefactor. Jacobian becomes very simple just as a prefactor, which is a number which tells you by how much you've blown up or shrunk. In other words, what's the slope of the derivative? It pretends to be a one-dimensional problem, even though z and f are both two-dimensional things, the complex number and complex function. That's number one. Number two is, what else can happen if you have a little shape and it's been blown up or shrunk? You can rotate it. That's the twist. And then one of these problems that you all stumble on and keep stumbling on is you're not allowed to include the reflection or complex conjugation in your discussions, because the moment you allow something to depend on a variable z and its complex conjugate, the whole magic is gone. You're not in a realm of analytic functions. Cauchy-Riemann is violated. Everything is two-dimensional, directions matter, etc. So you're not allowed to have a reflection. And reflection is, complex conjugation. Imaginary part goes to minus imaginary part. So you're allowed to rotate, but you're not allowed to flip. So that's the stupid problem that you're all stumbling on, apparently.
Okay. So I have a quick question about one of the things you said about the slope. So you said that the Jacobian has a prefactor. This is like how much you shrink or you blow up the shape.
Yeah.
So this is the Jacobian characterizes a transformation, right?
Correct.
And I guess in 1D, a function of one variable is like a transformation from the domain like x to the range y, right?
Yeah, and what happens in a process locally, you either stretch or shrink, depending whether the slope is larger than 1 or smaller than 1.
Okay. And so basically the slope in 1D is exactly analogous to the Jacobian in 2D.
Yeah, so slope is a one-dimensional example of a Jacobian matrix. Now in 2D in general, it's a matrix that we studied in the beginning of the course, which has two eigenvectors and two eigenvalues, and you have different action along them. So generally, Jacobian can be thought of some kind of ellipsoid, saying that there are directions, and in different directions, you have different stretching rates. But because you have direction independence of the derivative in complex analysis, you get a very special form of that matrix. That matrix can be written as a product of a diagonal matrix on which on the diagonal you have the same factor in both directions in your particular coordinate system, because there is no preferred direction. So as far as the magnitude of the complex slope is concerned, its absolute value is the same in all directions. So that's why R shows up. And that's analog of one-dimensional slope. But because you're in 2 dimensions, something does happen. And that says that Jacobian can be written as diagonal matrix with entry R, some scaling factor, times a 2-dimensional rotation matrix, because you're not allowed to change the magnitude, so it can be only rotation. But that matrix, has to have determinant 1, because normal rotation doesn't change orientations. If determinant was -1, you would flip the orientation. So that's not allowed. Amphi-TWYS doesn't allow it. It's really, really very simple application of what you did in the beginning with eigenvectors and eigenvalues. And, this amazing range of applications of which I'll spend, this week. This week I'll emphasize the applications that recur all the time in quantum mechanics, wave mechanics, electromagnetism, the number, and ideal fluid mechanics, the number of problems solved in the 19th century using these methods, which are, quite beautiful.
So when we see a mapping, do we basically treat it like a function? Like z, like f of z equals the result of the mapping. If you're going from z to
W, yeah.
To w, yeah, you treat it like w as a function of z, right?
Yeah, it's the image. Z is a kind of pre-image function, is a mapping.
Mm-hmm.
It just says that I take something in a z plane and it produces something in a w plane. And when you think of Amphi-TWYS, anything on the z plane gets put someplace on the w plane. That's called a mapping. So every point gets placed someplace.
Okay.
And that's a calculation. You know, there is nothing easy about it. I mean, depending how complicated your problem is, this might be a hard numerical calculation to find, you know, what's the image of your thing. Then there is discussion of infinitesimal variations in a neighborhood, and that's how we introduced Jacobians in the beginning of this course. It's a linear local, so it's an easy problem. It's a linear problem in a neighborhood of what is a complicated, difficult, nonlinear calculation. And that Jacobian just happens to be, if you have directional independence, it's fixed to have this, you know, amplitwist form. It takes kittens into big cats or smaller cats, and you know, they're disposed differently because, you know, they live in Beijing rather than living in Atlanta because of the map puts you there, so they're oriented differently. But they're still recognizable cats. They're not deformed.
Okay, thank you.
Okay, let's start with something that's familiar to you, Taylor series. But you know them for a variable, one function or one variable, but pair of functions, complex function of pair of very complex number. So when we do this in complex analysis, Taylor series refer to expansions about regular points. And what's a regular point? It's a point around which a derivative is defined. So it's a holomorphic domain of a function C. And last time I've derived a formula called Cauchy formula that says I could take a function, you know, I know what a function is, and I can complicate it by writing it as a contour integral around the pole. And, you know, what this combination of integration over 1 minus z does, it's really a generalization of Kronecker delta or Dirac delta operation for complex function. It says, let's take something defined any place in complex plane, and this is an operation in which I take that thing and I get it evaluated at one particular point. So that's Cauchy representation. You wonder, you know, why did we do this? Because I know what a function is. Why do I need to do this? Well, here is an example. I can pull out zeta and write this as zeta times 1 over minus z over zeta. Okay. Now what I can do is I can expand this as geometric series because I know that 1 over minus x is 1 plus x squared. No, so this is geometric series. If I do that, and remember, I'm allowed to do anything to complex functions, pretending that this two-dimensional object is really just one-dimensional. If I do that, then I get a series in z over zeta to the power k. And now I can exchange integration and summation. That needs to be proven. I haven't done it, but this is not a math course, so this is closer to engineering. So, you know, check it yourself in the literature. It's pretty straightforward. And now what I have is I have a sum of k, these powers, to all orders, that's k. There is zk from here, and then I'll multiply and divide by k factorial. I inherit 2 pi I because every contour integral has this prefactor, so it's correctly normalized. And what's inside of contour integral is a function f of z of zeta delta zeta, zeta to the k from here plus 1 from there. And now in the lecture, I didn't do it well. So if you insist, I can redo it. But this particular object is the representation of derivative of the function z. Just like this is representation of function itself. This is representation of its derivative. And it's being expanded in case around z equals 0. So this is a Taylor series. You're familiar from it in a real case, but it works equally well in analytic domain. And here is one thing that you knew already from Taylor series on the real line is that they're defined in the neighborhood of the point, and they don't, one Taylor series might fail you. They have a finite radius of convergence. And here it's prettier in complex plane. So this is convergent as long as the magnitude of z is smaller than some number r. And this r is the location of the closest pole of your function z. So this is a locally holomorphic function, but it might have poles. So there is a radius of convergence, r, and the contour is this, and all other poles sit outside. But the closest one defines what's in literature called radius of convergence. Then there is a whole, another set of lectures, which I will not do, but it's described in the textbook well enough. It's called analytic continuation. You can use your understanding of where the poles are, and you can move around your contour in such a way that you can make a Taylor series convergent on the larger domain, and that's very important in applications. So that's a complex Taylor series. It looks to the naked eye just like the usual Taylor series on a real line, but it's in a complex plane. So to understand how good it is, you have to understand what are singularities. So let's say it a little more explicitly. Singularities are of several kinds that you will encounter, and all of them have names. In the literature, they can be poles. So suppose your function is a rational function which has a numerator, which is a polynomial, and it has a denominator with poles. So now, because there is a power here, this is called double pole. This is just called a single pole or ordinary pole. And, this one pole lies in a complex plane on the real axis at value pi, and this one is up on the imaginary axis at value e to the, where e is a basis for natural logarithms. So that's the simplest example, and it has a property that you can define approach to the pole, one of these values, and that the magnitude, because derivative is defined in open neighborhood of this singularity, you can approach it in same direction, in any direction, And as you approach the pole, the value of the function diverges to infinity, but its neighborhood is isotropic. It doesn't matter how you approach it. So that's a pole. Now, what's not a pole that looks like a pole, and it's very important in electromagnetism and quantum mechanics in particular, are branch cuts. So branch cut looks like a pole, there is something up here, but it has an exponent which is not integer. Particularly important example, which I don't think I'll have time to do, but you can read in your textbook, is alpha equals square root. Important. Why are square roots are important? Because, the energy of mechanical systems is typically kinetic motion, like momentum square. So if you know energy, you want to know what momentum is, you take a square root. And when you do this in a complex plane, you end up looking at a branch cut, which looks very innocent, because what's the big deal with square root? But it's actually requiring quite a bit of thought. The functions are not, become multi-valued because you're taking square roots, so you could have two values, etc. So these are the innocent singularity. Poles are simplest, beautiful. All the Cauchy integration formula use poles. Branch cuts you see all the time whenever you have scattering problems of, for example, you're an engineer and you have to discover a cylinder in the water, in other words, the top of a submarine because you want to shoot it down. Then you have to deal with these branch cuts because you have to understand how the radar signal scatters, and that will be calculation that requires this technology. And then there are things that, we don't appreciate.
We don't only shoot things down, but...
I'm most of the engineering is beneficial to humanity.
I know aerospace has a particularly good job at shooting things down, but...
No, it's supported by the military to shoot down things, but of course we fly everything around. It's incredibly. It's like much of engineering and science, it's morally indifferent because it's just laws of nature applied. Now, how they're applied, of course, is an ethical issue, which we never teach in mathematical method courses. That's why I loved yesterday's colloquium. The speaker started with ethical issue. How do you deal with your co-workers in time of COVID-19? I loved it. Okay, so now, essential singularities, you cannot avoid them. They're strange. They're wild. And they're everywhere. So the basic idea of whole complex analysis is that you could define infinitesimal changes that didn't depend on direction and integrals that didn't depend on direction. That's where everything comes from. But what if your quantity is singular from some directions? But not others, So you see, you really have to work hard to get it. No, it's the first thing you write down. If you write exponential, not of z, but 1 over z, and in complex analysis, z is basis of everything, is complex variable, and you look at its powers and its inverses. So 1 over z is the first thing you do. So what if you raise 1 over z to potential, then what you can draw a modular surface. Remember, we had hard time drawing complex functions because they were in four-dimensional space, two results from two inputs. So we can't draw it, but we can draw three-dimensional versions of them. So for example, modular surface was one of these examples. We take the function and we just take the modulus. So we're in two-dimensional plane and we can draw its value. And now Z can be written as 1 over R E I theta. It's a complex number in polar representation. And only the real part matters, right? So you get that this becomes cosine theta over R, where theta is the phase of your complex number Z and R is its magnitude. When you look at this, now cosine can be positive and can be negative. If I look in a complex plane, this function, values of the function, when theta is smaller than pi over 2, then this is a positive number. So here the function grows very fast. The cosine is as large as possible. Close to imaginary axis grows not as fast. But on the left-hand side, this is negative, so the function vanishes. Here it grows. Not as fast or very fast because, I'm going to minus 1 over R or close to 0, which is not much. Now, what does fast mean? And that's a basic thing about exponentials, which I have to assume you understand. The exponential beats any power. Meaning, if I take this function 1 over x, so I'm looking at the cosine of 0, this fastest explosion axis, and I multiply it by x to any power, and I look at what happens as x approaches, as a positive number approaches 0, then this thing explodes because 1 over x is getting very large. And no matter what power, this vanishes. No matter what power I multiply, this explodes. Similarly, if I look at e to the minus 1 over x, this is going to 0, and I multiply by x minus k, so this is now a number that's growing when x is going to 0. So that's what's happening on the left axis. I find out that this is weird and strange and very important functions because on one side it goes whip, on the other side it falls down like a hole in the ground. And I've lost this magical property of holomorphic functions that it doesn't matter how I approach the singularity. So this singularity is called essential. And for example, it shapes my entire scientific life because there's an argument due to Freeman Dyson saying that perturbative expansion of quantum electrodynamics, things called Feynman diagrams, and the finest, the most powerful calculations that physicists have done in the last century about strength of magnetic moments, etc., due to quantum corrections. Dyson has a very simple argument saying the thing explodes because he can relate it to this particular function. And Predrag says Dyson is wrong. It doesn't explode because blah, 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 gauge invariance. So it's not just a little curiosity. All of the theoretical physics and all of the celestial mechanics depend on it because the so-called secular expansions, the ways in which you compute stability of n-body systems, solar systems, they all encounter the singularities. It's not a curiosity. Now, Taylor series makes total sense, but actually the object that's natural for complex analysis is something else, which is called Laurent series. And this is an expansion not about regular points where things are defined, but about singular points. In which the function of something, some variable approaching singular point is blowing up. That's a very strange object to do on the real axis because you would say, well, my function has exploded. Why would I expand around that? But in complex worlds, in a complex domain, everything is defined by poles, by singular points. And you find out that there are expansions which you wouldn't think of in a real case, which are totally natural. So here's just a simple example. If you take a function sine of an angle z, and for some reason you divide it by z over 6 because you're studying the black body radiation or something where strange powers show up, then you can always expand the numerator as a Taylor series because we knew that this is a holomorphic function. So the first term of sine will be z divided by z over 6 will be 5. The second term in sine expansion, there are only odd powers, is 1 over 3 factorial. Z cubed divided by z6 plus next term, which here has z to the 5th power divided by 5 factorial over z6, so that's 1 over z, plus, and now, the powers in Taylor expansion start dominating. So from here on, it looks like a usual Taylor expansion has a constant term, well, has a, powers of z rule. Now it turns out, because we now know about Cauchy integral representation, this is the most important guy, 1 over z, it's a simple pole. And this part of it here has a name, it's called residue. What is a residue? It's if you have any function and you find out how it behaves around the pole, then dominant behavior around the pole is 1 over z distance to the pole times some number that you have to compute for any given function, and that's called the residue. That's the important thing. So now if you take a contour integral of, what do we get? The contour integral, it should have been 2 pi in front, but I didn't put there, so it's here. And then the only thing that survives in contour integral, all the powers, negative or positive, they all vanish. Magic of simple or multiple poles. And the only thing that survives is this residue, 1 over 5. So, a totally non-obvious result. It would be very hard. You could, of course, do everything on a real line with sufficient skill. It's not obvious, but this integral, contour integral, is 1 over 5 factorial for any contour. K in complex plane Z with a singularity, in this case, at the origin. You're expanding Taylor series at the origin. So any contour that encompasses the line. And, there is another number, which we always have to have, number of windings, which in this case is just 1. So it turns out when you look at complex series, it's perfectly legal to have not only expansion in positive powers of Z, which is Taylor series, but actually any negative power is also legal. And if I have any kind of holomorphic function with a multiple pole M,
Are we to assume that M is an integer and this does not work for M is not an integer?
Yeah, everything is only integer because I warned you about branch cuts. The moment M is not integer, then the thing is called, the singularity has changed its nature. It's not a nice singular point. It's a branch cut, and you have to rethink it. Now, branch cuts have to be dealt with, but this all discusses nice singularities. So then, if you expand this in some kind of Taylor series, then I can go from K minus infinity to K plus infinity. And it's a series of this kind. So if this was holomorphic, meaning I can do it as polynomial or convergent function, Taylor expansion, you would have terms, and then there will be a term where I have, 1 over Z part, and that will just give me the residue. It'll pull out that coefficients in the series, and it goes on forever. Sorry, M plus 1, C minus A. The counter of such function will pull out the residue. Assuming that K winds once, and there is no other singularity. So that now has a name. It's used all the time, so people have given a name. So manipulation of this nature are called residue calculus. And in this particular kind of example, the residue of function, which can be expanded as a Laurent series, is coefficient of -1 term, because that what produces a pole that we need. Generalized Cauchy integral representation is very useful. That's why, we complicated our life by taking function and writing as a contour integral, because now for any function, we look at simple poles. So we look at where the interval, inverse of function is 0, because if pole is 1 minus z, 1 over minus z, then its inverse is 0. And we just pick up the residues of the function and all these poles. So this is actually how we label them, Z1, Z2, Z4 in a complex plane. And now we do our usual trick, which is we take a contour, we throw little bridges to the neighborhood of every complex thing, and we encircle them in the usual way, and then evaluate these local things. And now the rule says that when I'm in a W plane, the only thing that survives are the residues of the function evaluated poles. So let me just do a simple example of that.
So that symbol below the sigma, is that an equals, or are you trying to say inverse there?
I'm just saying the function, I pick a contribution at a pole where function diverges. And its inverse, then it goes to 0, right? Because it's going infinite. So that's just a mnemonic what values of z do I pick up? These are special values, these values which are little stars in a complex plane, in which the inverse of the function 1 over the, let's say, polynomial goes to 0 if it's a rational function.
Okay, so it means the z values where the inverse of f of z is 0.
These are the poles and not branch cuts and not essential singularities. Residue calculus only works on poles. It works on branch singularities, but one has to work a little bit more. And then amazing thing happens for the essential singularities. You can be stupid and you can just say, I don't know there is essential singularity. Let's just compute it as a series. And that's called asymptotic series. And we do it all the time in practical life. It turns out, I will do this in a lecture later on. Asymptotic series has a property that's really good, really good. So for example, in electromagnetism, we have computed an expansion to 10 orders in a coefficient called fine structure constant, which is 1 over 137. So we measure and compute the strength of magnetic field of an electron to 13 significant digits, and they agree. It's the most amazing prediction of quantum theory that's experimentally measured. 13 significant digits. So it's better than pennies in national budgets, etc. Agree. But Dyson says the series actually converges. It's asymptotic series. And indeed, after 137 terms, we computed only 10 terms. But if you computed 137 terms, it would explode, as I'll show later in the course. So all of these singularities are important, but residue calculus is the baby version of this, where I only have simple poles, dancing at funerals and stuff like that. What simple poles do. You probably don't know the joke. The joke is, no, I cannot do ethnic jokes in this course, so we'll have to do it when we meet in person. Okay. So now I've taken a few slides from Roman Grigoriev's lectures, so I give him credit here, but they're just standard things, it's fine. So let's take an integral from 0 to 2 pi of function of sine and cosine theta delta theta. This kind of things have to be computed all the time in scattering problems where I send a wave this way and it scatters, so I care about the angles, their sines and cosines. I do this all the time. Sine is a difference of two complex phases divided by 2I. Or if I'm on a unit circle in a complex plane, I can write it as z minus 1 over 2I. Now, why do I do this? I can start on a unit circle, but I know then I can change this contour in where it doesn't look like these complex phases. And, the cosine theta is the sum of these two guys, so it's c plus 1 over z divided over 2. And this integration, well, it's parametrization of the circle. So dz is a derivative of this, which gives me I e to the theta times delta theta. So that means that I can replace delta theta, this thing, by delta z I over z, because this is z. So in this way, you convert what is totally sensible trigonometric integral on a real line between 0 and 2 pi, the natural range of an angle, into a contour integral. It has minus I from here. There's a contour. It has my function, but now it's a polynomial in powers of z. And delta theta is, delta dz over z. So kind of brings a pole structure with this I in front. And now, if this is a sensible function, some kind of polynomial or something, turns out it's a series in terms of z's and 1 over z's. These are things that showed up in Laurent series, positive and negative powers of my variable z. The rule says, well, the result is known. The sum of the residues of this function. And the contour is, deformation of unit circle in which we haven't changed the number of singularities, simple poles within the circle. So for example, if the function is a rational polynomial, holomorphic function upstairs, a polynomial, things are falling apart in the studio here. The assistants are not helping. So, if I have a polynomial, I know I can always write a polynomial as a constant, the first term, the n term, times p minus the roots. So these are roots of the polynomial. And then how will I compute the residue? I'll have a sum. There'll be some kind of roots. At each root, this term, I cross it out and I look at the residue. And I evaluated this function for z being the value of the root. So very much like how the projection operators used to work in the very general matrix setting. And this is, really a projection operator on a subspace associated with each root. So here is an example. A simple function, trigonometric function, integral 0 to 2 pi over 1 plus epsilon times cosine. We make sure that magnitude of epsilon is smaller than 1, so this doesn't have a pole at all. And it's some function of these parameter epsilon, and again, you will be doing this often in various calculations in elasticity or many places where you have trigonometric functions. We convert this into residue calculation by writing this as cosine as z plus 1 over z over 2. I've done this, I brought it to this form of unit circle that I just showed you before. I brought it to this form. I've done all that. And now I multiply the denominator. So this is minus 2I over epsilon. You'll see where that came from. I multiply numerator and denominator by 2 over epsilon. And, from this term, I get z squared. From this term, I just get a 1. And this becomes 2 over epsilon c. So downstairs, I have a quadratic polynomial. It has roots. One of the roots has a plus sign here. This is just the usual quadratic polynomial stuff. Epsilon is smaller than 1. So this is a number that's outside the circle. But then I subtract this, and that puts us inside the circle. So this particular singularity is on the real line. It's inside the circle. This one, other one, z minus, will be the same, but with a minus sign here. So this is inside, this is outside. We can forget that guy when we're doing the counter integral. And what's the residue? Then residue brings 2 pi I with it always. And now, what we had here is z minus z minus. But because this factorizes in its 2 roots, but residue keeps the other root and evaluates it. When I add up these 2 roots, I replace the value of z by z plus. Now z plus minus z minus, this term cancels. This comes as a factor of 2. So this residue is 2 over epsilon, this part square root of 1 minus epsilon squared. The residue is evaluated value of z plus. And we get that this is a crazy result because, well, maybe not so crazy because we had a cosine, but we get a 2 pi divided by 1 minus epsilon squared, but this part, the discriminant. So that's an example of, how you integrate what might seem like a difficult integral. It just becomes that. Doesn't have a pole, epsilon is smaller than 1. If you have an integral of kind that we always encounter in our application, we integrate on a real axis. Very often we have to do a definite integral from minus infinity to plus infinity. Function is meromorphic. That just means it's a holomorphic except for some isolated poles. In the upper half plane, we're in a complex plane, and up there the function has at most some poles, number one. And number two, if as we go over to infinity make R very large, contribution falls off as magnitude of the vector to the second power as c goes to infinity, so make this counter long. Then we can split our counter in several parts. We can go from minus r to r, this stretch here, and take r off to infinity to get this integral, plus minus infinity. And then we have a circular half circle integral on the positive, on the upper plane in complex plane. And we look at it in limit, we go half circle, 0 to pi, in polar form. If our function, and that's, physically usually what happens, things that we are interested in are concentrated someplace. There's some charges, there's some masses, and their influence wanes as you go very far. If this goes like of order minus square in the magnitude, that will now defeat 1 power of r, it'll go like 1 over r. And we will find out that this part of the counter is what we wanted to compute, which is our integral I. And this part vanishes. If there were some singularities, for example, here are 2 singularities and plus and minus 1 as an example, then the integral will be 2 pi I residue of f of z in the upper half plane, as long as the contour is this contour here. And this integral we have to do very often. So that's why it got its own name, residue calculus. So for example, when you deal with propagators, Green's functions, solving Helmholtz problems on domains, charge distributions, drum surfaces oscillating, etc. Very often you have to do this integral 1 plus x squared. Now 1 plus x squared has 2 roots. They are at plus and minus I, indicated here. When you go in upper half plane, we only encircle one of them. So we get that the residue is 2 pi I. There used to be 2 factors when we factor it, but we're evaluating this at z equals plus 1 at this root. What's left here of the 2 factors, the residue is z, the other root plus I here. That becomes 2 pi I. This is I and this is I, so this is 2I. They cancel, and we get that this is pi. So that is a little bit crazy thing. We just integrate over rational polynomial, and we get a half circumference of the circle. But in complex plane, this is totally obvious.
I have a quick question.
Yeah.
That top integral on that page, the I equals integral of negative infinity to infinity of f of x, that could take the form of a Fourier transform, right? If you plug in
we're not allowed to do this yet. That will happen next week.
Okay. I was just wondering if that was a coincidence or not.
No, it's not a coincidence. Often it's solved by Fourier methods for the reasons which we know from our matrices, because there's translational invariance, so the natural basis of Fourier modes. But I'll explain what it means in more detail. And okay, I'll continue with these integrations on Thursday.